Okay, so as I mentioned, we have 2 more quizzes that are posted on Moodle. Make sure you take those. You could take them this week, or you can wait till next week if you'd rather wait. Quiz 4 is on sequential logic. Quiz 5 will be on timing analysis, and I'm hoping to add quiz 6 on digital building blocks, depending on how far I get today. So those are both due on the 3rd. Lab 4 is due on the 3rd. And make sure you demo your Lab 3. We don't have information or an upload link yet for Lab 4 demos, but we should have that soon. And next Monday is our last lecture, so this is just 2 more lectures, and labs will be running normally next week, but they're canceled this week. Okay, so at the beginning of the semester, I talked about what a logic circuit is, and I said that it has inputs, outputs, and a functional specification, and also a timing specification. But I didn't talk about what that is, and I said that I would come back to that. A timing specification is, for combinational circuits, it's the propagation and contamination delays of the combinational logic circuit. And for sequential circuits, it's the minimum clock period assuming a given clock skew. Okay, so I'm going to define those here in just a minute. But before I do that, let's talk about behavioral versus physical. So behavioral, like when you simulated with Model Sim, you were simulating the behavior of your circuit. You just wanted to know if it worked correctly. There was nothing in the Model Sim simulation about timing. Model Sim basically assumes that your circuit runs infinitely fast because it's only testing the behavior. But there are physical considerations that are very important that you need to consider when you deploy your circuit on an FPGA or an ASIC. So for combinational circuits, so for example, like I mentioned, there's time required for signals to propagate through the circuit, which is, as I mentioned, called logic latency or delay, or propagation delay and contamination delay, which I'll define here in a minute. For sequential circuits, it's the clock rate. So you're all familiar with, when you buy different CPUs, they have they're rated for different clock rates. Power consumption, energy per unit of computation, which is energy efficiency. Thermal dissipation is how hot the device gets, and the real estate required, how much real estate on the chip you need to deploy the circuit. So we haven't considered any of these things in this course so far. Yes?
What is real estate here?
Area, chip area. So in the case of an ASIC, it's the physical space that you need to use on the die. Right. And then on FPGA, it's the number of resources on the FPGA you have to allocate. Right?
Number of LUTs?
LUTs, yeah. Okay, so when we did the simulations in Model Sim, the Model Sim assumes an epsilon delay, meaning that if in this case, we have a circuit where A, B, and C are the inputs and Y is the output. And so in this case, you can see that in this case, we change, the first time the output changes is here. And the reason it changed is because with an input of 1, 1, 1, the output is 0. And I think with all other input values, the output was 1, right?
It's kind of counter.
Yeah. Well, yeah. So A, B, and C were counting. They were counting from 0 to 7, and then it repeats. So we were basically testing every possible input, and so you can see that when A was 1 and B was 1 and C transitioned from 0 to 1, that's what causes our output to drop. But when that happens, it happens seemingly at the same time. And in fact, when you look at that, you're almost like, wait a minute, how do we even know from this timing diagram that Y dropped as a result of C rising from 0 to 1? I mean, they're happening at the same time. It's almost impossible to tell that there's a causal relationship there, right? Because in Model Sim, it's like instantaneous, right? And in reality, of course, it's real logic circuits aren't that fast. And the reason is because you have in a CMOS logic gate, you have capacitors that are formed on the inputs, because the inputs of the gate go into the gates of transistors. And CMOS transistors form a capacitor between the gate and the substrate, the bulk node, right? Also, there's also capacitors that form between the source and drain of the transistor and the substrate. So there's capacitance there. There's also even capacitance in the wires, and then there's also resistance in the wires. So basically the delay for a gate is essentially the product of the capacitance times the resistance. So what happens in reality is that when, like for example, if this is a buffer where you've got A is the input, Y is the output, and this is just an identity function. And so when A goes from a value of 0 to 1, Y will also go from 0 to 1, but there will be a delay, right? Now, typically the way you measure the delay, because in addition to having a delay from the input to the output, you also have a delay in terms of rise time and fall time, right? So, because you notice how A sort of goes up at a slope, right? As does Y. So generally the way that this delay is measured is from the midpoint, from the middle point when A hits the halfway point between 0 and 1, and when Y hits the halfway point between 0 and 1. And then you measure the delay as the difference in time between those two events. Yes?
So in case there is 5 volt to 3 volt logic, you just get maximum voltage multiplied by 0.5 and get your point in time when the value when the A signal is on that value.
Right.
Okay.
Yep. Okay, so there's actually two kinds of delays. There's propagation delay and contamination delay. Propagation delay is the longest amount of time that you'll see between an input changing and the output changing to reflect that change of input. And then there's a contamination delay, which is the minimum amount of time where you'll see that change happen. Now, you have to keep in mind that not all changes in input will actually change the output, right? So this is assuming that you're changing the input in a way that does make the output change, right? Okay, so you might say, well, wait a minute, why? Well, two questions. First of all, why would we care about contamination delay? Because that's just why would we care about the minimum amount of time? It seems like we should be more worried about the maximum amount of time it takes to propagate an input through a logic gate or a logic circuit. And the other question you might say is why are they different, right? Why is propagation and contamination delay, why do we have two different delays? There's a whole bunch of reasons behind this. So you can measure propagation and contamination delay for a single gate or a whole logic circuit, a whole combination of logic circuit. So if you're talking about a single gate, then it could be because there's a different, the time it takes for a gate to switch its output from 0 to 1 is longer generally than the time it takes it to change it from 1 to 0. And that's because the PMOS transistors that are responsible for setting the output to 1 are weaker than the NMOS transistors that are used to drive the output to 0. Right? It's just something that you get with CMOS gate technology. Also, if you have a complex gate, when I say complex, I mean like a 3-input gate, for instance, or a 4-input gate, or something like a mux cell, where if you have a 2-input mux that's built with transistors, which is typical in technology libraries and cell libraries. Sometimes a 2-input mux is considered a gate. Then you have different paths even internally, different wire lengths inside the gate or the cell that the signals have to travel along to go from input to output. Also, there's a difference, there's some temperature dependence as well with CMOS gates. They tend to be slower when they're hotter. Now, the more obvious, though, reason why they'd be different is if you're talking about not just one gate, but a collection of gates that are connected in a schematic, like a whole logic circuit. And in that case, the reason why they're different is because you have different pathways through a circuit. You have short paths, and then you have long paths, right? So a signal may come into a logic circuit and only go through a few gates, or it may go through more gates depending on which of the inputs you've changed. Okay, so here's an example of that. So here's just a real simple circuit, has 3 gates, and you can see that there's the longest path is between A or B and the output Y, because in that case you have to go through 3 gates, right? That's called the critical path, right? And the shortest path is from D to Y, right? So the shortest amount of time the contamination delay for the entire circuit is going to be the contamination delay for just this gate, right? So every gate has a contamination delay and a propagation delay, and then the whole circuit can have a contamination delay and a propagation delay. So with regards to the whole circuit, if we calculate the contamination delay, or the shortest possible path through the circuit, it's going to be the contamination delay of just this AND gate, right? But the propagation delay of the whole circuit is going to be the propagation delay of the AND gate plus the delay of the OR gate plus the delay of the AND gate, right? So in other words, what you're doing here is finding the shortest path through the circuit is the shortest possible delay. If you look at technically, in this case, I'm assuming that well, actually, it's not an assumption in this case, because it's got to be, you know that the shortest path is going to go through this AND gate, right? So it's the shortest path is going to be the shortest amount of time from the time you change an input to the time you change to the time the output updates is going to be this path. So again, it's going to be the contamination delay of this circuit, whereas the longest will be, adding up the propagation delays of those 3 gates. Yes?
But even for one circuit, is it statistical thing, like under different conditions, even through the shortest path, you may have a delay, contamination delay a little bit different because of temperature, of noise, etc.
Yeah, that's true. Generally, you'll notice, like in the FPGA tools, I don't know if you've read the output from Quartus, but it actually refers to, they have delay models for the FPGA at different temperatures. And when they report delays, they use the worst case temperature, which is usually 85 degrees. They have an 85-degree Celsius model. And they consider that to be the highest temperature you'd operate the FPGA at. But the caveat there is that in our we don't run it anywhere near that high of a temperature. So the FPGAs will tell you what the delay is, and it's kind of a pessimistic number. So I have done this quite a bit myself, where I overclock. You can overclock your FPGA circuit. You can run a little faster than what the tools tell you, because it's determining those delays, kind of worst case delays. Okay, yeah, so I just want to point out the notation here, though. So we have T sub PD, the propagation delay of the whole circuit, is going to be 2 times the propagation delay of the AND gate plus, because there's 2 AND gates on the path, right? Plus 1 propagation delay of the OR gate. And then the short path is the contamination delay of the whole circuit, which is the contamination delay of the AND. So I want to just point out that in the critical path, we're looking at propagation delays of the individual gates, and the short path, we're looking at the contamination delay of the individual gates, right? Okay, so I mentioned that this can get kind of complicated, because you have to look at, when you're running a timing analysis on a circuit, logic circuit, the number of possible paths can be can be quite a bit, right? It can explode. Yes.
Graph algorithm, directed graph algorithm, find the shortest path and possibly find the longest path to each point.
Yes. Yeah. You could use that. Yeah. Yeah. Sure. Certainly. In this case, so you've got a lot of paths through here potentially. The reason I point this out is because I'll ask you a question on the exam. It'll say, basically you'll have a circuit like this and you have to find the short path and the long path through the circuit. And so you have to consider, different paths through the circuit. So anyway, yeah, so the idea is that the number of paths is essentially the number of inputs, but for each input, if there's any fan outs in the circuit like we have here where this gate fans out to this fans out to two places, then you have to consider that as well. So you add up 2 to the power, or for each input you add up basically all the fan outs along that from that input. Okay, so there's also this thing. I mentioned that contamination delay is the soonest you can expect an output to change when the inputs are changed. And so generally what that means is that it just is giving you a range of propagate. The time it takes to get a signal through a circuit is a range that's between the contamination delay and the propagation delay. But sometimes you'll encounter this thing where you'll change an input and the output will actually change multiple times within that range between the contamination and propagation delay. Like you'll have a circuit, you'll change an input, and the output will change twice. Like the circuit will be a 0, you change an input, it'll go to 1, and then it'll go back to 0, and that'll all happen it'll happen after the contamination delay but before the propagation delay. And if that happens, that's called a glitch. And glitches are fairly common. And they're a result of the way that you build your circuit. So an example of that is if you have this circuit where we've got 2 AND gates and an OR gate, and assume that A and C are 0 and 1, and then B changes from 1 and then goes to 0. Okay, so what that means is that the input is 0, 1, 1, and we're going to change it to 0, 0, 1. Okay, so in other words, we're just changing B. Right? Now, that should not change the output at all, because the output, if you look at the truth table, is 1 for both of those cases, both of those input values. Right? But the problem is that when you change B has this fan out, right? So the value of B goes through this inverter, and then it goes through the AND gate, and then goes to the OR gate, which is the longest path. That's the long path, the critical path, right? But it also goes through the short path. Goes through this AND gate and then that OR gate. Okay, so what's going to happen is when you change B from 1 to 0, that makes the output of this AND gate switch from 0 to 1, because you had basically 1, 0 going in there, and then you're going to change it to 1, 1, right? Make sense? Then the bottom AND gate is likewise changing, but this time it's going from 1 to 0, because it was 1, 1, and you're changing it to 0, 1, right? So if you look at these 2 intermediate signals, N1 and N2, that are coming out of those 2 AND gates, they are going to change at different times, right? Because this AND gate is going to lag behind this AND gate because there was this inverter, right? The B had to pass through the inverter before it got to the top AND gate, but it didn't have to do that for the bottom AND gate. And so if you look at the timing diagram, N1 is, they're both toggling, but N2, the bottom one, is going to be ahead of N1. And there will be a brief amount of time in there where this OR gate will see, the OR gate is going to see initially 1, 0, which gives you a 1 output, and then it's going to briefly see a 0, 0, right? Because this guy, the bottom input was a 1. That was what was sustaining that OR gate's 1 output. But it's going to drop right away, and the OR gate is going to see a 0, 0 until the top AND gate catches up and then puts a 1, and then you'll end up with a 1, 0 in there, right? So what will end up happening is you'll see this glitch. Now you might say, wait a second, why is the glitch not? It should be aligned over this part where they're both 0, 0 inputs. Well, yeah, but it's not. The reason why the glitch has moved out to the right a little bit is because of the propagation delay of the OR gate. Yes?
Are there any algorithms to detect glitches, or we just need to try any input combination?
Well, there is. In Model Sim, I don't know if you guys have seen this yet, but every once in a while a Model Sim will actually generate glitches even in your system Verilog designs. It's really weird when it happens because you'll be testing your CPU and you'll see a spike on Model Sim that lasts less than, like literally a spike. And I don't know how it detects it. That's a good question, especially since you're giving it Verilog code. But sometimes you'll actually get, it'll detect it. But like I said though, it's not a huge deal because if the glitch happens, it should still be happening within the two, after the contamination delay and before the propagation delay. So the propagation delay by the propagation delay, the output should be stabilized, right? So you shouldn't have to worry about glitches as long as the circuit is timed for the propagation delay. Now there is a way you can fix glitches though. I mean, at least in some cases. I don't know if this is, if there's a universal general fix for these, but and I got this from the book. I thought this was kind of neat. It's not super practical, but it turns out that in this case, the reason the glitch was happening, you can explain it because if you look at the Carnot map of the circuit, what was happening was we were going from 0, 1, 1 to we're going from, I think here, which was 0, 1, 1, and we were going to 0, 0, 1, right? Like, because B was changing,
yeah.
Right? So B, so basically A and C were staying the same, right? So in the Carnot map, because C was changing the same, so we're not going to change rows, right? Because that would change C. And then A is not changing. A is staying 0, right? So you're going from this to this on the Carnot map. You're going from this cell to this cell by changing B, right? And so it turns out that you can mitigate that if. So the problem is you're basically leaving one Carnot grouping and going into another. So if you add another Carnot group that covers that transition, which would require you to add another AND gate and another input on the OR gate at the end, right? What will happen is that when you pass from these two cells, you'll stay within a group. You won't leave one group and go to another group, which will add some redundancy to the circuit, but it will prevent the glitch from happening. Which makes sense because the whole reason the glitch was happening was because the OR gate, had that little period of 0. But it turns out that, as I mentioned, it's not a big deal. It's usually something that you can just live with, at least if you have a synchronous sequential circuit. I think you asked about why don't we use asynchronous circuits. Mm-hmm. This is the reason we don't use asynchronous circuits, because if you have a glitch in an asynchronous circuit where there's no clock, glitches are devastatingly bad because you get that glitch and it puts you in a state you don't want to be in. And so this is the whole reason we don't use asynchronous design. Okay, so now in addition to gates, So far we've just talked about combinational logic. Now let's talk about sequential logic. Flip-flops also have a propagation delay and a contamination delay. Because, why wouldn't they? It's just their logic circuit, right? Now the notation is a little different though. The notation the book uses is TCCQ and TPCQ to stand for the contamination and propagation delay. Make sense? It's kind of weird, right? Remember before it was TCD, right? CD standing for contamination delay, and TPD standing for propagation delay. But now it's CCQ. I don't know what that stands for. I just see the C in there. It just means
Contamination sequential, propagation sequential.
But there's no S though. I think Q means it's like the output of a register is usually Q, but why is there two C's?
Sequential.
I don't know. Unclear where that came from. But just remember it's CCQ, PCQ. It's pretty obvious because there's a C and a P as the first letter of the subscript. Okay, so we've got that. Now we'll come back to that in a minute. I'm going to change and move on to another slight topic change here. We talked about flip-flops and how edge-triggered flip-flops, in theory, sample their input D on the rising edge, right, say, or on the falling, on an edge. Usually, in this class, we usually just use rising edge, right? And so I always, in the case of you guys, when you do your behavioral design in Verilog, you just assume that the flip-flop takes a snapshot of its input on the edge, and that snapshot is an infinitely small amount of time, right? So it like instantly, samples the input, right? But it turns out that's not true. That's not how they work in reality. Every flip-flop has a parameter called setup and hold time, meaning that you have to keep its input D stable before the clock edge for an amount of time called the setup time. And you have to also keep it stable after the clock edge called the hold time. If you add the setup time and the hold time, basically that creates an aperture that is around the clock edge. So you got the clock edge, and then you got this time before and this time after the clock edge. And again, the clock edge is measured from the halfway point. So, when the clock is transitioning from, say, low to high, and it's a 5 volt, say it's a 5 volt signal, when it hits that 2.5 volt halfway, then there's a time before that setup and a time after that, which is the hold, and the time that time span is called the aperture time. You can't change the input in the aperture time, because if you do, it could cause the flip-flop to become metastable. And what that means is that the flip-flop will actually generate an output value in the forbidden zone, meaning between 0 and 1. But it won't stay there forever.
Next clock edge?
No, sometimes not even. It'll go in the forbidden zone, but it will eventually, and even possibly before the next clock edge, within the clock period, possibly, it'll settle back into an output, right? But the time it takes to do that is it's an exponential random variable, right? So we don't know. Could be within the clock cycle, could be after, but suffice it to say, if you go to the metastability, then you can throw the contamination delay and the propagation delay of the flip-flop out the window, because there's no more promises, right? If you become metastable, you can't, the flip-flop is no longer beholden to this stated contamination propagation delays, right? It just goes, now it doesn't permanently damage them, and it doesn't brick your device. It just puts it in this weird in-between state for a while, right? Okay, so oh yeah, sorry, I should have showed this. So this is a picture of, there's a clock, and there's the D, this is the input, and again, the setup is before the clock edge, the hold is after, and then the time, if you add those two, it's T sub A aperture time, right? Make sense? Okay, so you don't want to change, ideally you wouldn't change anything in the aperture time. Yes?
Is there a way to define the setup, hold, and the setup time and hold time based on how gates connected to the flip-flop?
Yeah, it's all technology dependent. Yeah, it depends on not only the design of the flip-flop, but also the technology, the semiconductor technology. So this is one of those things that's going to improve with Moore's law, basically. But it's a function of the underlying technology. So unless you're in the fab, unless you work in like your fabbing chips, or you don't basically have any control over this, right? You have to just take it. You have to take these numbers from the spec sheet, from the technology sheets, or the data sheet, and go with it. Okay, so now you might say, what is the point of all this? Well, what this comes down to is this thing called dynamic discipline. That basically means that if you have, your gates all have a contamination delay and a propagation delay. Your flip-flops have a contamination delay and a propagation delay, and your flip-flops have a setup and hold time. Now, you're the CAD tool, and you're going to take system Verilog and convert it into a gate level net list, a gate level schematic. So when you do that, you have to then report back to, you have to do some kind of timing analysis on that circuit and report back to the user, the designer, essentially what the maximum clock rate you can run this at without violating these numbers, right? And this is called the dynamic discipline. As long as you adjust the clock rate such that you don't violate the setup and hold time after you calculate all your propagation and contamination delays, right? Then things like glitches aren't going to affect you, and you can reasonably guarantee the user that the circuit will work, right? Is the idea. Make sense? So this is another part of what's going on when you guys when you compile your design. A lot of people think, well, there's a lot of expensive problems that the CAD tools have to solve. One is parsing your Verilog and converting it to gates, but then you have to take those gates and map them onto the flip-flops. Then you have to figure out where you want to place, which LUTs you want to map them onto LUTs, rather. Then you have to figure out which virtual or logical LUTs that you're going to map onto which physical LUTs you want to use to map your logical LUTs, right? And then you have to make connections between them, right, in the routing fabric. And then you have to run this timing analysis and tell the user how fast the circuit can run, right? Or if they try to, if they tell you, I want it to run at 100 megahertz and it can't run at 100 megahertz without violating the dynamic discipline, then you have to report that, right? The CAD tool has to report that, right? So this is another part of the synthesis process.
How many synthesis reports when you load your design, even if it does, it's hard to see something.
Yeah, I know. And the bigger problem is, and this is a problem I've struggled with my entire career. Let's say it doesn't run as fast as you want it to. Then what do? Well, that part's tough because basically it's going to tell you what the paths are that violated it. So whenever you generate a timing report, the timing report is all going to be in terms of inputs and output paths, right? But these are paths that are in the synthesized circuit, not necessarily in your Verilog. I mean, you might figure out where that corresponds to in your Verilog, but you have to keep in mind that your Verilog was translated first to gates, then these paths, exist in the gates, right? So it's not always straightforward how to restructure your Verilog in order to fix these. I mean, generally the case is you add pipeline stages. That's generally how you approach the problem. You add registers to break up long paths. But that part is the part that's kind of more of an art than a science, kind of, because you got to, figure out how to go in and tweak your design. Okay, so let's go into a little bit more detail here. So if you have a synchronous design, synchronous designs, for example, pipeline or the finite state machine type designs that we looked at in the last lecture, they have a bunch of paths that are going to begin with a register and end with a register, or flip-flop, right? Okay, so within each clock cycle, that blob of logic that's between these two registers is going to have a propagation delay and a contamination delay. And that propagation delay and the contamination delay have to include the impact of the registers too. So you have to add, for example, when you're looking at the long paths, the propagation delay of the flip-flop or register, right, added to the propagation delay of the logic, which is the longest path through the logic, right, and then likewise for the contamination delay. Okay, now in the case of the propagation delay, if you have a specific clock period in mind, which is T sub C, this is the clock period, this is the reciprocal of the clock rate, right? So, if it's a gigahertz clock, it's a 1 nanosecond clock period, right? So this is in seconds, TC, right? So that's the time between, the rising edges. And so you have to make sure that when you're calculating the long path, that you don't violate the setup time. In other words, the time it takes to get through here plus the setup time has to be less than the clock period, right? Because you have to get everything into this guy, not by the edge of the clock, but by when the edge of the clock comes backing off the setup time, minus the setup time, right? So you got to go from here to here, including the propagation from here, the propagation from here, and the setup for this guy, right? On the other hand, is the hold time. You also have to make sure that this logic isn't too fast. Because if it's too fast, what will happen is this guy will change on the clock edge, and then the logic will percolate through here too fast, and you'll violate the hold time of this guy, right? Because you got to make sure that this circuit can't be too slow, but it can't be too fast. Because otherwise, this input is going to change before the hold time expires, right? So if that happens, well, then the only way to fix that is to go in and add buffers. You got to add delay somehow. You got to add redundant gates to make that. You got to make it slower, right? But if it's too slow, the only way you can do that is make a longer TC, meaning slow your clock down, or change your data path so you change the data path in a way that reduces the propagation delay. Yes?
If there is a possible violation of hold time, doesn't it signals you that there's probably something with your design and you should restructure it?
You shouldn't have to do anything about hold time violations. However, that being said, I have gotten errors from particularly the Xilinx tools. I get hold time violations all the time. And I usually don't know what to do about it. But the more common ones are setup violations, because that's something you can do that's easier to take care of. Okay, so more generally, the TC, and this is just a formalized description of what I just said. TC has to be greater than or equal to, this is the clock period, right? The time you give the logic circuit has to be greater than PCQ, that's the dumb abbreviation I mentioned earlier, that's the propagation delay of the flip-flop, plus the propagation delay of the circuit, which again, if it's a complex circuit, you got to find the critical path through that guy. That's going to be, don't get confused. Remember, TPD can refer to an individual gate propagation delay or a whole circuit, combinational circuit. So this is the whole circuit we're talking about, plus the setup time. Right? So these three added together have to be enough. The clock period has to be enough for these three guys added together, right? And then this is just, now you might say, well, can I restructure this? Because I can't change the clock. Let's assume I can't change the clock. I have a clock frequency I want to hit. And obviously I can't change the propagation delay of the flip-flop or the setup time of the flip-flop, because those are technology dependent, right? I have to live with those because that's the fab technology I'm targeting. But I can change the propagation delay because I can restructure my circuit. So I want to put that on one side of this inequality, because that way I have an idea of what my constraint is. This is a constraint, a timing constraint. And so this second equation, inequality, is just moving things around from the first one. Okay, but you can as long as you can do algebra on here, but it's basically the same thing. Okay, and then likewise, as I mentioned, the whole time. Now you have to be careful. This can get a little confusing. The whole time has to be less than the contamination delay from the originating flip-flop, which all the flip-flops have the same contamination delay. But what we're talking about is the time this guy takes to update, the minimum time this guy takes to update, plus the contamination delay of the logic circuit, which is the short path, the shortest path, the fastest path through the circuit. Okay, so the hold time has to be less than that, right? Why does it have to be less? It has to be less because I don't want to change that input too soon, right? And again, you can restructure this inequality and put the contamination delay on one side. So the contamination delay must be greater than, meaning that I have to slow down my circuit, possibly, by adding stuff, has to be greater than the hold minus the contamination delay of the flip-flop. Okay? All right, so here's an example. So let's say we have this, here's an example problem. Let's say we have this circuit. So this is a pipeline, basically, or data path, like a pipeline stage, for instance. Input registers, output registers, blob of logic in between them. And we have the following characteristics. We've got T CCQ, T PCQ, that's the contamination propagation delay of the registers, T setup, T hold, and then per gate. Now, we're assuming in this case that all the gates have the same propagation delay and contamination delay. It's usually not the case, right? It depends on the gate. But in this case, we're going to simplify this and just say every gate has the same. But I may ask you a question on the exam where I may actually have different delays for each gate depending on what the gate is, right? Because obviously a 3-input gate is going to be slower than an inverter, obviously, right? Just it's a different type of gate. Okay, so what is the what do I have to figure out? I have to figure out if this will work. I need the clock. Where's the clock speed though? I need the clock time too. TC. Do I have it? Oh, right. Yeah. No, actually, I don't have the clock. Right. I don't have that yet. Right. I'm going to figure out what my clock can be. I'm going to find out the limits of my clock. That's the goal. Okay. So I don't know what the clock rate is. So the first thing I want to do is figure out, what's the T PD and TCD of the circuit. Okay. Well, obviously, since all the gates have the same, pretty much the shortest path is going to be, if I start with contamination, short path, right? Is this guy, right? Through here, right? So I'm guessing the TCD has got to be, it's probably just going to be 25 picoseconds, right? Likewise, the propagation is going to be, 3 times, right? The propagation delay, so 3 times 35, right? So yeah, 3 times 35, 105. CD is 25. Okay, so I got those. So my setup time constraint then is going to be, my clock has to be greater than or equal to the propagation delay of the flip-flops, right, which is 50, plus 105, that's the logic, plus the setup time, 60, right? So that's 215 picoseconds, right? So my clock has to be greater than, or my clock period has to be greater than or equal to that. Likewise, and that, by the way, is turns out to be if you take the reciprocal of that, 215 picoseconds is 4.65 gigahertz, right? The hold time is going to be the contamination plus of the flip-flop plus the contamination of this guy, right, of the logic, the short path, the single gate. So it's going to be 30, right, 30 plus 25, right? And that has to be greater than, right, which is, 55 picoseconds. In other words, 55 picoseconds is the shortest amount of time before this guy is going to get an update on his D input, right? But that has to be greater than the hold time, right? Well, the hold time is 60. So this circuit is not going to work because we violated the hold time constraint. Now, the setup time, remember, has the clock involved in there, right? Because the setup time is giving you, basically is a way to determine the clock rate or determine, whether the clock period is sufficient. But the hold time doesn't have the clock is not part of the hold time calculation, right? We don't care about what the clock speed is for the hold time. So it turns out that, we violated the hold time constraint. Yes?
You can add to the critical path, for example, one inverter and replace that NOR with regular OR.
Yeah, I think that's exactly what they did. Instead of adding, you could add an inverter and change the gate, but they just added a buffer here. So basically, what the buffer did is it's going to change the contamination delay to be whatever that guy's contamination delay is, which is 30 plus 2 gates, which is going to be 25 times 2. That's going to be 80. So this is, by adding this, it's going to boost the contamination delay up to 80 picoseconds, which is fine because the hold time is 70, right? So we're in good shape, right? So so we're good. Okay, so there's one other complication that we have to consider, okay? So you got the clock. The clock comes into the FPGA or the ASIC, and it connects to every single flip-flop on there, right? So the clock network is large, big. There's a lot of metal that comprises the clock network, the clock signal, the clock net, right? The clock has to connect all this stuff, and it's a lot of wire. And that creates a lot of, that's a lot of capacitance. And what ends up happening, unfortunately, is that if you looked at the clock at different points on the chip, it's not going to be synchronized because the clock may be delayed in one part of the chip versus another part of the chip. Yes?
Can you have, for example, some oscillator in the center, and then in equal parts, it will be the same delay, like equidistant from the center with head?
Yeah, but it's still going to depend on where you are relative to the center, though, even if you did that. But I mean, generally, the way the clock works is it comes in, clocks are always generated with a crystal, they're piezoelectric, yeah. And then the piezoelectric oscillators are usually limited to about 250 megahertz. And then you might say, well, if that's the case, how do I have a 5 gigahertz CPU? Well, it comes on the chip, and then they are able to multiply the clock on the chip. But from the multiplier, right, which is an analog circuit, phase lock loop, out to the rest of the chip, you have this thing called clock skew, which basically means that there's going to be, basically a different version of the clock at every point on the chip, right, in terms of timing, right? They all look like a clock. They're all 50% duty cycle, but shifted, right? That's called clock skew. And so you have to incorporate the clock skew into this timing constraint as well. So generally, the way this works is you assume a maximum clock skew, essentially, and then you do your timing calculations based on the maximum clock skew, and you build that into your calculations. So basically, the impact of that is when you do your setup time calculation, you have to add the clock skew as a fourth parameter when you're calculating the data path delay. So you've got propagation from flip-flop, propagation from combinational logic, setup time, clock skew, right? So you have to add that as a fourth parameter. But aside from that, everything is the same for the propagation delay. Make sense? Now, you might say, wait a second, why are you adding? Why are you always adding? If you don't know, clock skew says that the clock may be delayed where you are, may be late, right? Now, what are we really measuring? Well, we're measuring the difference in the clock between the two endpoints, actually, right? So, for example, if this guy had a late clock, and this guy has an early clock, That's a problem for propagation delay, right? Because this guy is going to put his output out late, and this guy's going to expect it early, right? So that's why we add that here. This time t sub skew is the maximum difference between the clock at the two endpoints, right? However, with the hold time, it's kind of the same principle, but in reverse. Let's say that this clock was early, and this clock was late. Well, this is going to give, if this clock is an early clock, because he's closer to the clock source, the clock pins, if this register is placed closer to the clock pin, and this register is farther away from the clock pin, then this guy's going to get a head start, which means that when this signal comes rushing through this logic into this second register, this destination register, it's going to get there early, right? Meaning that we might violate a hold time constraint because of that. So it's the reverse, right? As compared to the propagation delay. So in that case, the contamination delay of the flip-flop and the contamination delay of the circuit added together have to be greater than the hold time, which is what we had before. But then add the skew. In this case, we add the skew to the right side of this inequality. We're adding it to the hold time. In other words, we're building onto the hold time. We're saying, well, the hold time was 60 picoseconds, but the clock skew might be 20 picoseconds. So I'm going to add that as an additional constraint to the hold time. I'm going to make the hold time more constrained, basically, to account for the skew, right? And again, you can restructure this and have TCD, which, again, the reason why they want to put the TCD on by itself is because that's something as a designer you can control. None of these other things you can't control the skew, right? You can't control the technology parameters. So we're going to put the CD by itself and basically say the contamination delay must be greater than the hold plus the skew minus the contamination delay of the flip-flop, right? So this is just the same thing, but just putting the thing that you can actually control as a designer on one side. Okay, so, all right. So basically, when you synthesize your designs, the CAD tool is going to tell you whether you've violated the setup or hold time. Now, you might say, wait a second, I haven't seen any violations in our design yet. Well, that's because we set the clock constraint. We told the CAD Quartus that the clock is going to run at 50 megahertz, which is a 20 nanosecond clock. You might say, well, where'd you say that? Well, it's in the project file that we gave you. I don't know if you guys have that project file. The way Quartus works is the project file is a QPF file. You open the QPF file, and then the QPF file is like a 3-line text file that points to a QSF file. And the QSF file is a script written in Tickle, the tool command language, which in part of that is the clock constraint is actually inside that file, and that's where it tells Quartus that it's 50. And it turns out that the crystal oscillator on the DE2 board also runs at 50, so we don't have to multiply the clock. We just use the raw clock. Yes.
I believe there is in a top design somewhere like this. There's also like several clocks, and we just picking one.
Yeah, you know what? I don't know. That's a good question. The old DE2 boards just had one clock. When we got the new DE2 boards, there's 3 clocks. I think they're all the same clock, but I think they come in 3 different pins. But I don't know. Philip, do you know why there's 3 clocks?
There's 3 clocks because there's 2 crystals on the board, one for, I think, like 20 megahertz, one for 50 megahertz, and then they have a 3rd clock on there specifically for the AV outputs. That's a 25 megahertz clock.
Yeah, but I think isn't there 3 50 megahertz clocks too?
I mean,
I could be wrong about that.
Okay, that may actually be, there may just be 2 50 megahertz clocks and then the 125 megahertz one that's for the AVs.
Yeah, when I first started using the DE2 boards, I was afraid that we wouldn't even be able to make the 50 megahertz clock. So we were using the 25 or the 27, and then at one point we said, let's just try the 50 and see what happens, and no one ran into issues. But I think then it turned out that 50 wasn't a big deal, so you guys didn't run into any problems because your designs are still relatively simple. But anyway, you might say, what about the skew? Where's that come from? Clock skew, I think that's part of the FPGA library that's built in. I think Quartus knows that because it knows what FPGA you're targeting. And well, actually it's a combination of the FPGA plus the packaging of the, what kind of package it's in, the ceramic, package. I don't know, it knows that somehow. I never really looked into it. But it knows what the clock skew is, and the clock speed is something that we give it with the QSF. Okay, so what about the buttons on the board? The switches? Because you guys have switches. So basically the CAD tools, when it synthesizes your logic, if you've got a data path from one register to another, it can synthesize that and it can do a timing analysis and make sure you don't violate the dynamic discipline, meaning it doesn't violate the setup or hold time. But if you have a switch on the DE2 board hooked up to a register that you're flipping as a human being, well then how does the CAD tool guarantee that you're not going to flip it within the aperture time of the flip-flop that it's connected to? Now you might say, well, you have to flip it, I don't know, what's the likelihood of that? It's actually a little higher than you might expect it to be, actually. No, yeah, well, there's a debouncer, but even with the debouncer, it's non-deterministic. You don't know when the CAD tool has no control over when the user flips that switch, and if that switch is connected to a flip-flop, there's no guarantee that you won't put that flip-flop into metastable mode, into a metastability. So how do you deal with that? Well, okay, there's a couple things. First of all, let's just assume for a minute that you do put a flip-flop into metastable mode. Okay, how long? I mentioned to you that it doesn't stay in there forever. It will eventually stabilize. It just goes wonky for a while. How long is it wonky for? Well, it turns out that the time that it's wonky is basically it's based on a exponential. It's an exponential function. So if you look at the probability that you will achieve your result within a certain amount of time t, right? So t sub res is the time to resolve, meaning it gets out of metastability. It goes back to normal. The time that the resolution time is greater than a certain t. Sorry, I might have said that wrong. The time that if the probability that the resolution time is greater than t, meaning that if you give it t seconds, it's still going to be wonky, can be calculated as e raised to the negative t over tau. And tau is a technology parameter. That's something that's a result of the actual design of the way that this flip-flop is designed, and also the fabrication, the CMOS technology, the silicon technology that implements it. Okay, so tau is something you're given. Okay. So the next question is, okay, well, what is the probability then that? Now, by the way, just to give some context here, you might be saying, why do we care about this? Well, what I'm about to get to, just to set you up a little bit for this, is t is eventually going to become the clock period, right? So ultimately, we want to know is if this thing's going to get out of metastability by the next clock, right? Which is what you were asking about earlier. Okay, so that's what this is all about. Okay, so the question then is, well, what is the probability then that we'll go into metastability mode? Well, that's actually pretty simple. Now, I'm assuming that we've got a button tied to a flip-flop, right? So you got a user hitting the buttons, right? So you have no idea when they're going to hit that button. In other words, when they hit the button, they're going to change the input, the D input on the flip-flop. We don't know when they're going to hit it, but in general, not knowing that, what's the probability that they're going to put the flip-flop into metastability? Well, that's easy. That's the aperture time divided by the clock period, right? So the lower, so if you, the smaller the clock rate, right, that's going to give you more edges per unit time, right? And the aperture is situated around the edges of the clock, right? So if you have you have the aperture time and you have the clock rate, then you can calculate the probability that you'll randomly hit one of those apertures, right? Because, basically, the higher the clock rate, the more apertures you have, the more potential violations you can have, right? So the question then is, if you multiply that, you multiply the probability of getting into the metastable mode times the probability that you'll be out of it by the next clock period, you get this. It's basically t sub 0 over tc times e to the negative t over tau. Now, t sub 0 is the aperture time, basically setup plus hold time. That's technology dependent, as is tau. Tau is characteristics of the circuit that determine how long it's metastable for, right? So you're always going to be given these two numbers, right? And so t sub c is, the clock rate, clock period rather. You plug that in, right?
May I have a question on the
Yes.
first slide?
Yes.
How do you multiply the probability of input, the probability of going to the metastable and the probability of going out of metastable?
Well, we're trying to get to the point where what we're going to do eventually. Well, I'll get to that here. Let me go to the next slide. Point this out. So where we're going with this is we're going to add a synchronizer. So a synchronizer is an extra. We want to add an extra flip-flop between the flip-flop that we normally want to use to capture the input and the switch, the button, right? You add an extra flip-flop, and then all we have to calculate then is two things. We need to know the probability that the first flip-flop, the synchronizer, will become metastable, because it's like it's sacrificial, basically. We want to say, we're going to put that in there, because if that first flip-flop goes metastable, as long as it resolves itself in the whole clock cycle it has from that time to the actual golden flip-flop, which is the one that we actually want to sample into our design, then we're fine. Right, then we're fine. Now, what happens if it doesn't? If it doesn't, we got a problem. It's going to fail. But at least we can calculate the mean time between failures, and that's what we're trying to do with this, right? So now you might say, wait a second, why don't we just consider the first flip-flop the synchronizer? Well, you don't want to do that because you might have some logic before that, right? The goal here is to have a whole clock cycle. The objective here is to have a flip-flop with nothing after it going into another flip-flop, because that gives you that whole clock cycle with no logic. You don't have to worry about logic in there, right? That gives you the whole clean clock cycle for that first guy to get out of it. The whole point of that is not to have anything between those two flip-flops, because then you maximize the amount of time that the random variable has that determines the metastability time to get out of it, right? And that's the whole point of a synchronizer, is just to do that. Now, it's not a guarantee, though. There's no guarantee that you won't basically fail and violate the dynamic discipline by virtue of just having someone hit a button on your computer. Okay, so like I said, that's the synchronizer. It's just basically a dummy flip-flop. So button, dummy flip-flop, and then your real flip-flop that's going to be the input to your design. And then, like I said, after your real flip-flop, you probably going to have logic there, right? So the whole point of this is to have no logic in between these two guys, right? Okay, so you have a clock edge. So basically, let's say you get a clock edge and this guy becomes metastable, and he's going to be metastable for a while, but he's going to stabilize eventually, hopefully, by the setup time for this guy, right? So how much time do you have? Well, if he goes metastable, you have the clock time, TC, minus the setup time, because you don't want to, you still have to have it stabilized for this guy. You can't violate his setup time, right? So basically TC minus T setup, that's your time. Remember the first equation I showed you had a T, that's what you're going to use for T. So this is what captures everything. It's going to be TC minus T setup. Previously I just had that as T, right? But now, why am I substituting that? I'm substituting that because I want to know, I'm basically giving it a time limit, right? I'm giving you have to get this done within TC minus T setup. We still have tau, and then of course you have that first argument there, which is basically saying, if you're going to calculate the time between failures, you have to calculate two components. The first is that you'll go into metastability on the synchronizer. That's one. And we multiply because it's an and, both have to be true. And it's got to also not resolve itself within TC minus setup. So we got to have two things go wrong. One, the user hits the button at the wrong time. And two, this guy just randomly just takes too long to go out of metastability. So those two things together will give you this expression, which is the probability of having a failure. That's assuming, of course, you have one synchronizing flip-flop here. Okay, so the mean time between failures then is just the reciprocal of that term. However, you have to also consider another factor here too. The free rate at which you're hitting the button, right? So I mentioned that, you know, like if you have the clock rate, the higher the clock rate, the more apertures you have that potentially you're going to nail. But obviously, if I only hit the button once in a while, right, it's not as big of a deal as if I, do this, right, hit it really fast, right? The faster you hit it, the more chance you have of hitting it during one of those apertures around one of the clock edges, all right? So that's the n. So if the input changes n times per second, that's how fast you're hitting the button, the probability of a failure then is going to be n times the aperture time, t0, divided by the clock rate, multiplied by e to the minus tc minus setup, that's your time limit for the synchronizer, times tau.
Like
right?
By order, so you have n cases and you OR them, and that's why you add, right? Like n multiply.
Yes, yeah, for the n, yeah, you're right, yeah, that's exactly right, yeah. Okay, so here's an example. So assume, let's see, suppose TC is a 500 megahertz clock, that's 2 nanoseconds. So, about 10 times faster than the one that we're using. Let's say tau is 200 picoseconds. Why is it in seconds? Well, that's the parameter, it's in seconds. Tau is, the units are tau is seconds. It's basically the average time it takes to get out of metastability on an exponential distribution. It's the mean of the exponential. Okay. Then t sub 0, look, that's also seconds. Why? Well, aperture time. It's aperture time, seconds, right? So t sub 0 is 150 picoseconds. T setup time, also seconds. Although, yeah, t setup, we have to have t setup because that's part of the time limit. And then n is 10 events per second, right? So if you just plug all those in, you can calculate both the probability of failure and the mean time between failures. The probability for failure is 5.6 times 10 to the negative 6th power. You might say, well, that's pretty good. But then if you take the reciprocal of that, it turns out to only be 5 hours, which means that on average, you're going to get a bad input into your circuit every 5 hours.
So the lesson, don't hold the key on the keyboard when the computer freezes for 5 hours, right?
Well, the problem is it's not even that. It's if you have a like a network connection coming in, right? Like if you have a network connection on a network interface card, you've got packets coming in. They're going to come in at a very fast. Those bits are going fast, and you have to capture them inside your network interface card, and you're capturing them on a clock. You have the same issue. It's not just buttons. This applies to any I/O device. Anything that you can't control in terms of the design of your computer is going to fall into this category of this unpredictable nature and having to capture it. So now to be fair, I think in a network card they probably have multiple synchronizers to try to reduce that even further. But there's always a chance that you'll have again, it's just the nature of this, the flip-flops.
I believe they also have some and some checksum at the end of the
Yeah. Yeah. There's also protocol level checking. Yeah. Okay, so that's it. That's the whole timing lecture. Speaking of timing, 5:09. I timed that perfectly. Any questions?
Can you please go to that formula when we have probability, the initial P?
This one?
Yeah. First question is why is this formula called? The second question is what is the tau, like time constant for how fast the pulsation with stability? Where do you get that? It is given?
Tau, it's given, yeah, it's going to be given. But tau is the mean. So there's basically the time it's going to take to get out of metastability is just a exponential distribution. Mm-hmm. And that's the mean. It's the average. It's basically the average amount of time it takes if you put a flip-flop into metastability. How long on average is it going to take to come out? That's all the tau is. And T0 is just the aperture time. I used to be confused by those. I was like, what? Where are those coming? But that's it. They're pretty obvious. It's just one is the average time you're in metastability, and the other one's the aperture time.
I should listen more carefully in the course of statistics.
Yeah, well, I mean, it's just exponential. It's just the longer it's very. So basically, in all likelihood, it'll come out of metastability very soon because the exponential is very high on the left side, and as you go to the tail on the right, it's very low. So there's a very small chance that it'll be in metastability for a long time, but the chance is there.
There's a formal proof, and we had it as an exercise, but except that I remember not much.
Yeah. Yeah, we used the exponential a lot more in my other class, 317. You probably, you're a grad student, you probably won't take that.
No, not in this company.
Oh. Yeah, we use it in queuing theory too.
Can you please explain about, well, you said that PMOS are weak, P-type and MOS transistors, PMOS transistors are weaker than NMOS. Why so? I don't get it.
It's the mobility of the charge carriers in the P type are slower, and so you can make the P mosses bigger to try to compensate. But if you do that, it increases the resistance. I think it doesn't increase the resistance. It increases the capacitance. Capacitance, right? So basically, you have to make, because the mobility, meaning the charge carriers in the P-type silicon, which are holes, they are physically they're about half the speed of the electrons. That's just you can't overcome that, and so you have to balance that by making the PMOS bigger. But in doing that, you increase the surface area of the gate, which increases the capacitance. So you have to charge. It takes you more time to charge up the gate of the PMOS, and as a result, the rise time is going to be slower. It's going to take longer to drag the output of a gate up to 1, whereas if you want to make it 0, you turn on the NMOS transistors, and because electrons are so fast, they pull down fast. So that's why you get the rise time is different.
But how increasing chip area will help improve speed characteristics of the holes in the chip?
It doesn't. It allows you to, if you have, if you make the PMOSs bigger, or if you make all the transistors bigger, you can improve the discharge rate. You can strengthen the drive of the gate, right? But you still have that fundamental difference between the N and the PMOS time. That's the problem. I'm not sure. Hopefully I explained that right, but
maybe I unintentionally keeping all people in the class.
Oh, okay, yeah, yep. Okay, well, we're all set. If you have any questions about the quizzes, let me know, and if you need any help with the labs, let us know. And have a great Thanksgiving.